where is the second one? Here. So this is the continuation of your education on how to use the MyDeck. It's just that this time you're going to use a couple of very interesting, tools, an oscilloscope, okay, and a function generator. For this one, you're going to have to use that black connector that you're going to push carefully on the side of your MyDeck, okay, because this black connectors contains screws to hold the wire. So you push the stripped wire in it, then you turn the screw, okay, and that will hold that connection properly, so it doesn't keep getting off and you be losing signals. So as you see right here, you have analog outputs. You have two of them, and that is the ground for the analog outputs. Analog inputs, you have 4 of them, 0 plus, 0 minus, plus 1, minus 1. Okay, you have here power supplies, plus 15, minus 15, and these are the grounds for these power supplies. On this side here, you have digital outputs. You have 8 of them, starting at 0 all the way to 7. Okay, and these here are going to receive a value between 0 and 5 volts. And as you see right here, you have a 5-volt power supply associated with digital circuits. So what did I do here? Well, I said I'm going to get the output of my function generator on output 0, say analog output 0, and I'm going to connect that to analog input 0 plus. Now I have made the connection because the output here is from the function generator, but the input here is for the oscilloscope. So let's take a look at these devices. So here is the function generator. You are capable of generating 3 different kinds of waveforms: a sinusoidal waveform, a triangle waveform, and a square waveform. This button here allows you to set the frequency. This button here allows you to set the amplitude. In this one, what is called the DC offset. You can think of the DC offset as, suppose that your ground is at 0, okay, and you decide that you want that to be at 3 volts. So you change the DC offset, so now your waveform is going to be centered on the 3 volt line instead of on the 0 line. So it just allows you to shift the waveform up or down. As you see here, you can go to plus 5 or minus 5. The amplitude can be set from 0 to 10 volts. You can also use these analog, dials here for you to be able to do that. This part here we don't use very often because this is basically for you to create what is called a, in other words, you want to change the frequency starting at 100 ohms all the way to 100 hertz all the way to 1000 hertz, okay? And you want about 100 steps. So the device is going to compute what it needs for you to do to be able to go 100, then a fraction more, and then keeps going up and varying the frequencies in this amount of time. So, and that should take 1000 milliseconds, which is basically 1 second. So in 1 second, your frequencies is going to start at 0, then go all the way to 1000 hertz. Again, this allows you to select your device, and this tells you where your signal route is. Remember that I showed you that we were doing analog output 0 because we defined that right here, okay? This again allows you to run the, the function generator continuously. And this here is for you to run these sweep settings, okay? You also have a help right here that you can use to be able to find out things if you are you're not understanding what is taking place. Now, this is the oscilloscope. The oscilloscope basically will look at the waveform and is going to show the how can I say, the shape of the waveform. So as you see right here, this is a sinusoidal waveform. Okay, and basically I got that from the function generator, and now I see my sinusoidal waveform here. This is very much like the waveform that you have on your outlet in your house. All of the what you call it outlets will output a sinusoidal waveform. Okay, and the what you call it the magnitude is 110 volts. In Europe, it's 220, 240. Okay, so depending where you are in the world, that may change. And you have two parameters here that you need to worry. One is the number of volts that you have per division. That is defined here on the vertical position. So you'll be able to calculate what that is, because if you know the number of what you call it volts per division, suppose we had set this to 1 volt per division. Then I have 1 volt here, 2 volts, 3 volts, 4 volts, almost 5 volts. Okay? The one on the horizontal line is time. Okay? Time is the inverse of frequency. So F, frequency, is equal 1 over time. Time is equal 1 over frequency. So if I'm able to set the time right here, suppose 0.2, let me see, right here, time division. If I say 5 milliseconds, then each and every one of these markings here is going to be 0.5 milliseconds. So I have 0.5, what you call it, no, that is 5 milliseconds, I'm sorry. 5, 10, 15, 20, 25, okay? 25 plus 25 is 50 milliseconds. So if I go on my calculator, I can compute what that frequency is. 1 divided by 50 milliseconds is going to be 0.05. That is a 20 hertz signal, okay? So that is how you look at these types of signals. And you could experiment and do something like, okay, you connect a microphone or maybe some music from your telephone to the MyDeck, and you could see your music displayed here. Okay, usually music and speech are complex waveforms that will go everywhere. Okay, but in reality, that is basically the sum of many different sinusoidal waveforms with different frequencies, different amplitudes, and different phases. All right, so again, a few more questions for you to look at and to answer, okay? In all of them, you basically, if you have to take a picture, you put it down here so that you'll be able to see what is going on. And in all these years, okay, most of my students that really apply themselves, okay, to perform this have had no difficulties. In reality, some of them look at me, why are you making it so simple? The reason why it's made so simple is because many of you have never operated this type of a tool. So I have to really start on the bottom and bring you guys up. So some of you, there are a little bit more, how can I say, knowledgeable of that. You know, what you can do is you can help some of classmates, you know, and be helpful to them. Because somebody that teaches, he's learning more and more about what he's teaching, okay? The more I teach to you, the more I learn, okay? So that is an important thing. All right, so that's experiment 2. Now let's take a look at experiment 3. Okay, let's see, share screen. Which one is experiment 3? Man, I'm getting old and blind. Using my deck 2, using my deck 3. That's the assignment in Moodle, downloads. Okay. Share. I think this is it here, guys. Let me see. Oh, yeah, this is it. So in this experiment, you're going to start using some more interesting devices. Some of them are linear, others are nonlinear, like the diode. And I'll be getting some diodes to give it to you guys. So I will not penalize any one of you that you didn't do this part here because of that. But then you should do this later for you to learn what the diode does. The diode is an interesting device as it allows current to flow through it if it is forward biased. Okay, that is a bias for the diode. If you swap the leads, okay, it becomes reverse biased, and then it does not allow current to flow through it. This is a very important thing because that function allows you to change a signal from AC to DC, which is in every power supply that you have. The cool thing about the diode is that it emits light when current flows through, so you would be able to see that here. You have another diode, but it's not an LED. Therefore, you will not be able to see the light, but you can perform the experiment. Now, this tells you how the diode is set up. That is the length of the leads of the diode. This side is called the anode. This side is the cathode. If I make this side here A positive, and I make the K side negative, then the diode is forward biased. If I reverse that order, I make A negative and K positive, then the diode does not conduct any current. And that is part of what you're going to do in this experiment. The other thing that I want to go through is this right here. Come on. Oh, man, I thought it was here. Right there. Sorry. This here is called the proto board. Okay. And the proto board has wires under these holes that connect these holes. So this column of rows right here, holes right here, this one, these 5 holes are connected together. These 5 are connected together. These 5 are connected together. So if you notice, when I put my red wire here and I connect it to the power supply, that also means that this lead of my diode is connected to 5 volts. And then I get this lead here from ground. That means that this side of the resistor is connected to ground. And then now I have this lead of the diode connected to the resistor. Therefore, I have this circuit right here. My power supply positive coming in here, my diode right there, followed by my resistance right here that goes to ground. And you see that I use these characteristics of the proto board to be able to build this circuit. The cool thing about this board, this prototype board, is that it is solderless. You can insert the parts into it, okay, and prototype your circuit, test it, and then you can make that into a fixed circuit by creating a printed circuit board where the the elements are going to all be soldered to the board. But this is for prototyping, and it's very good for you to learn because you may have several circuits during this semester that you're going to be using this. Now, this on the outside right here, they are connected differently. They are connected horizontally. So this hole all the way to this hole are connected together. This hole all the way to this hole is connected together. And so are these, that, and that. There is a gap right here, okay? What most people use this for is to use them as a power bus. So I could make, for example, this row right here, okay, ground. So I would connect this from that to ground. I could make this row right here, 5 volts DC. That would be my 5 volts DC bus. But remember, if you're gonna use both sides, you need to connect them here in the middle because right here, there is a gap. This side is not connected to this side unless you make it so. Same thing down here. And many a times you forget to do that, and usually your circuit's not going to work properly, but it's very easy for you to find out if it is working properly or not. You basically get your multimeter and you test the ground and the VCC connections or the positive voltage connection of every one of your devices until you find that one of them don't have it. Okay, then you know, okay, that means that my power supply is not there. And then you end up coming back to this point that say, oh man, I forgot to put my wire here. And I have seen that happening many a time. And it did happen to me many years ago when I was first learning how to use this type of proto boards. These are circuits containing resistors. We already talked about that last week. Okay, these are circuits containing parallel resistors. We also talked about that last week. Okay, this is the total resistance. 1 over the total resistance is equal to the inverse of the resistance, the sum of the inverse of the resistances. In here would be circuits where you're looking at mixed circuits. Well, let me tell you the easiest way for you to solve things like that. First, tackle this part of the circuit right here. These are two resistors in parallel. So you apply the formula R3 times R2 divided by R3 plus R2, and you get the value of the equivalent resistance. That equivalent resistance is going to be in series with R1. And because they are in series, you just add them. So these kind of circuits are easy for you to simplify. But the important thing is, at first, it is better for you to draw it all out and make the simplifications, okay? And then you will get the idea, and that is going to be reinforced as you solve more and more problems. Okay, so here's an interesting problem, okay? How can I connect two batteries that the overall voltage is 0? As you see, these here are AAA's or AA batteries, right? So I have this one here. I connected the negative side right here, the positive of this one to the negative of that one, and the lead of the multimeter on this side. Therefore, I get a voltage from here to here that is equal to the addition of the two voltages. So 1.5 volts here plus 1.5 volts here, I should read 3 volts from here to here. The question is, how can you make a combination of two batteries that the result is equal to 0? So that is something for you guys, okay, for you to figure out what is going on in terms of that, okay? This here, on the other hand, is called a parallel connection. In this here, that means that you have more capacity. So if this here allow me to have 1 amp per hour, putting another one in parallel increases that to 2 amps per hour. Okay, so it increases the capacity or the ability to provide current. Okay, this increases the voltage, but the capacity remains the same. Many times when you guys see NiCad, or not NiCad, lithium polymer batteries, they are usually connected in a series parallel configurations. Do any one of you guys have remote control devices like airplanes, what you call it, copters, quadricopters, or cars? Any one of you? No?
I do.
You do? Well, you saved the whole class, because I was going to ask you guys what kind of a childhood you guys have if you never had a remote control device. They are a lot of fun, okay? And especially for people that like to build things, it's really cool for you to build one of these aircraft, okay? And better part is to go fly, learn how to fly, and evidently you're going to crash many times. And you're going to, by the time that you finish learning how to fly, your aircraft is going to have a tape all around the aircraft, okay, because you have, crash a few too many times. But it is fun. Okay, so this is basically the end here. There is a challenge here where I ask you guys to combine resistances to be able to achieve this goal right here. That in this. So this will be most probably series parallel configurations, where you have some resistors that are in parallel and some that are in series. Now, is there any questions from you guys?
Yeah, I have a question about experiment 1.
Okay.
So for that one at the bottom, you have to submit your sources that you used for how the ammeter and ohmmeter and voltmeter work. Is there any particular format you would like us to put
I don't care of the format. I just want you guys to get used to, because if you don't do that, you are what you call it, copying information from somebody else. So that is what I want you to do. I want you to recognize that, okay? And you cite the sourcing, that will be fine.
Okay, thank you.
Okay, I always believe a lot in getting you guys to do some research in things like this, because you end up doing a lot of learning by doing things like that. And through your student career, that is going to repeat itself many, 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 many times. Any projects or any things that you will ever do is going to require you to do some research. You already have done that in high school, and evidently many teachers, especially the English teachers, can be very critical about the way that you cite your sources, okay? But that is just a part of the learning, okay? Because there are more than 100 different ways that you can do those things. So to me, I don't care very much how you do it. I just want you to cite the source where you got that information. Okay? All right. So any other question?
I saw that for this experiment they just went over, there was a light bulb. I didn't have a light bulb in my little packet. I was wondering.
Don't worry about that. That one was just to give an example of a circuit. Okay, I wasn't asking you to do this here. That is just to show you what a flashlight is. So basically you have your flashlight right here, you have your batteries, you have this spring here on the bottom that puts pressure on the batteries to make contact here with the one side of the bulb, okay? And you see that this metal connect comes around, okay? Here you have a switch. Okay, that switch will turn it on or turn it off. And then when you complete the circuit, current will flow through and the lamp is going to become incandescent, and that is going to generate a what you call light, okay? But this kind of what you call it, filament bulbs are really going by the way of not being used anymore, because they are they are short-lived, okay, and they use much more power than what you can get, for example, with an LED. So most probably you guys have in your houses is still some flashlights that contain incandescent filaments, but most of them are being substituted now with flashlights that contain LEDs. Even the lights that you use in your house, you have many different types, you know, the fluorescent type, you have the incandescent filament type, and you have the, what you call it, LED type. Well, people say, well, but the fluorescent and the LED type are more expensive. Yes, they are a little bit more expensive, but the price is coming down. But the important thing that you're not looking at is that incandescent filament light bulb only works for 800 hours. The other two is about 5,000 or 8,000 hours. So when you do the accounting of the amount, you're going to see that they operate at a much lower rate than does the incandescent filament. Some places in Europe and some other locations in the world no longer allow incandescent filament bulbs to be used. Okay, so that should be something that you should be, how can I say, pay attention to. One of the good things that it does, it gives you more money because you have to pay less to the electric companies, okay? And any money that you can save is a good thing, you know, however small that amount it is. So any other question? That's a good time to pick my brain, guys.
For experiment 1, I literally have no batteries in my dorm. Like I searched my entire room and I found one battery in my remote, and that's it.
Well, then you showed one battery for your thing. I'm not expecting that you guys need to go out and buy batteries, okay? But for example, if you go home, okay, on the weekend, I bet that you have a whole bunch of batteries at your parents' home.
I mean, I really can't go home. I live like 6 hours away, so.
Okay, Shane, use whatever.
Just the one battery is fine then?
Yeah, you can open your car key things and you have a battery in there. Everything will have a source of power, guys. Okay, so one is fine. I don't have a problem if you are not able to find many more. But the important thing, why am I asking you to do that? For you to learn how to measure a voltage. That is the whole purpose for that. After you learn that, then the measurements will become second nature for all of you. One thing that you have to realize is that all the voltages that you measure, I beg your pardon?
Oh, sorry.
Okay, so the important thing is that every voltage measure that you make is across a device. Is from one side of the device to the other. Every current measurement that makes, okay, you have to break the circuit because what you're measuring is what is flowing through the wire. Okay, so always make that differentiation. Current, you measure what is going through the device. Voltage, you measuring what is across the device. All right, any other question?
I have a quick one. I hope it doesn't come across as too dumb. So just whenever we're doing experiments, the reports are basically just a paper with all the questions answered and everything. That's all it is.
Yeah, you can use these papers that I provided you in every location that you have read, okay? You put your answer right here. That's all. I made these on purpose that way so that you don't have to worry about creating a special document. You already have the document. You just have to record your observations and so on and so forth. Okay?
Alrighty. Thank you.
And that makes it much easier for everybody. The first year that I did that, the students really loved it and said, Mr. De Souza, it's really easy. And this one is a keeper. In other words, keep doing it like that because it makes it simple for all of us to work. So, all right. So other questions? Oh, and by the way, the only stupid question that there is the one you don't ask. That one is really stupid.
Do you love me?
I agree.
No, I don't love you.
Thank you.
Okay.
Oh.
This is really, how can I say, childish of you.
Oh.
Yeah, man, that was whack. What the heck?
Okay, can't you guys grow up? You still haven't left high school yet? This is college. And this form of behavior, okay, is really not cool. When are you going to grow up? What's the matter? You don't talk anymore? All right. I'm sorry about this, guys. There's always people that will do this kind of stuff. I mean, they never grow up. They're going to be 40 years old, 60 years old, and they're still going to behave that way. All right. So, any questions for me?
Yes, sir. For like the time period for our labs, is it just like time set aside for us to work on it like by ourselves, or do we have to join somewhere?
The laboratory, as I told you guys, I said, I made the laboratory times with the TAs in case that you have questions. So suppose that you were at home and you started working on your experiment and then you got to a question, you say, oh boy, I don't know how to go, what to do here. Then you can go talk to the TA during the laboratory time and the TA will give you a hand. Okay, that's all that is. But if you don't need that, you don't have to go to the lab.
Okay, so I was just making sure it wasn't like mandatory.
No, it's not mandatory. I don't make anything mandatory except this class here. This one is mandatory because you have to answer your attendance. simply because this class was created where attendance is 50% of your grade. But that's why you all are here. Okay, but no, I don't make anything mandatory. You know, the people that want to learn, they will do whatever they need to learn. The people that don't want to learn, no, that's their problem. There's nothing that I can do. If you don't want to learn, there is nothing that I can possibly do because you don't want to do it. That's what it comes down to. So, any questions?
My question. So after we answer the PDF, you want us to save it and just upload it to Moodle with our experiment?
Yes, you can. You can save it as a PDF, or you can submit it as a doc file too. The format is not what you call it important to me. The only thing that is important is for you to submit this report with all your answers. That's what I want, because I cannot give you any points if I don't get this report. Okay? And as you guys have seen, these are not really hard experiment, guys. Okay? So the important thing is for you guys to do it. Any other question?
How much, like, is that grade gonna bring us down? Because my email messed up and I couldn't get it submitted on time.
Well, you know something? You are an engineer. You know what the how can I say, the amount of the percentage or the grade distribution is, and you know what grades you have, and then you can calculate that. Now, if you are unable to do that, what the hell are you doing in engineering?
All right, I got it. Thank you.
Okay. Anybody else has a question?
I have a question. If we do our experiments late, do we get half credit? If we miss it?
No, I don't
just
give
not
half
do it at
credit.
all?
The due date is the due date. You either do it before or you don't do it. I don't believe in doing things late, guys. Either you do it by that time or you don't. That is the due date right there. This thing about, oh, yes, I'm sorry about this and I'm going to give you extra time, then I would rather put the due date at that extra time instead of doing it and then have to be observing that people are submitting it late. I don't want that kind of work. You either do it or you don't. It is your choice. All right, any other question? Clarify everything that you are not aware of and that you need to know. That's a good time for you guys to do that.
Mr. D'Souza,
Yes.
for the resistors for experiment 1, I got like 2 of the same values. Like
Yeah,
resistors.
if you put those 2 of the same value